The objectives today, we're going to demonstrate how the Arango Data Science Suite can help with fraud detection in an online marketplace. And I'm going to showcase how the Data Science Suite can accelerate the productivity of data scientists by streamlining the sort of machine learning ops workflow and the machine learning development process. For this demonstration, I'm going to use a data set that contains marketplace product listings that emulate your problem. Those product listings might be legitimate, but they might also be counterfeit, and we need a way to automatically identify counterfeit item listings before they're listed on the site. So by the end of this exercise, we should have seen that we're able to predict whether a seller's item is counterfeit or not using graph ML, graph machine learning, and how we can provide a natural language query interface so that site administrators and content managers can interrogate the data without having to be AQL or Python developers. So I'm sharing my notebook here. These are what's called a notebook. We use notebooks as a primary interface for data science. They're very popular with data scientists. We host the Jupyter Notebook service, so all that you've got to do is just focus on developing your applications. And we use notebooks as a kind of a mission control that drives the analysis and the orchestration of the data science services. Now, notebooks are composed of different cell types. So in this example here, we've got, for example, we've got text cells or descriptive cells, documentation cells in text. And in fact, this one is, we can use Markdown as well, as you can see here. And we also have Python cells in which we can run Python code. And as part of that Python code, we also define things called magic functions, which are like shorthand, which effectively allow the data scientists to abstract away some of the underlying complexity when they're making calls to these machine learning services. So let's dig into the use case. But before we get into that too much, we can take a look at the tools and technologies that we'll be using for today's demonstration. The Arango Data Science Suite is built on the foundations of the Arango multi-model database. It's distributed, it's scalable, it's highly performant. It provides very rich graph database functionality, provides full support for JSON documents and key value data types, and it includes powerful features like integrated text search. And so our customers, they really benefit from not having to deploy and manage and pay for 3 separate database technologies. But built on top of that, we've got our graph capabilities. We've got our graph query capability that allows developers to query and traverse data that's contained in a knowledge graph stored in the Arango database. And it also provides the foundation for the data science suite, which is made up of graph analytics, graph machine learning, and Gen AI. If we look at the sort of the typical workflow of data science and how we support that, we load our data into a knowledge graph. We run some graph analytics on that data to identify some logical groupings within that data. And then we can train our models to identify fraudulent products in the listings as they appear. And lastly, there's the Gen AI piece where we provide a natural language interface for, as I said, for administrators and content managers to query and interrogate the data that's in the listings that make up the marketplace offerings. We need to better satisfy this kind of scenario here. We're going to have millions of items for sale, so we need to be able to automatically identify fraudulent or counterfeit items, and we want to be able to remove those products automatically. It wouldn't be feasible to do it manually at that scale with potentially millions of or hundreds of thousands perhaps of fraudulent items appearing. And as I said, we want to give those site administrators the means to answer natural language questions like, tell me who are the worst offenders, or what's the worst location for bad sellers. If we take a look at the data model of the data set that we're using, we've got the website in green at the center, as you might imagine. And then we've got, in relational terms, we've got a sort of a one-to-many relationship between the website and the products in red that are being offered for sale on that website. And then another one-to-many, we've got sellers in yellow, and the products that they're offering for sale on that website. And if there's any, we can have additional information in these blue vertices here, for example, if there's additional information about those sellers. We can take a look at one of those products. We've got one here. This actually happens to be, it's a watch, but it happens to be a fake watch. It's already been identified as counterfeit. There's a bit of a clue here in that the image that we're looking at of the watch, it's not from the manufacturer's website. It's just from a sketchy S3 bucket in AWS. And that's just perhaps one of the indicators that we might use then to identify whether an item is fraudulent. We've also got information about the item itself. So we've got things like the currency and the price and where it's being sold. And again, this is information that we might use, and we'll come to that in due course. Before we do anything else with this data, we need to make this data usable to the machine learning process. And for that, we're going to use Arango Data Science Suite, Graph Analytics. We need to be able to group the data that's in our graph into entities. It's called entity resolution, in fact. And the algorithm that we're going to use is called weakly connected components. And that's just one of many of the capabilities of our Graph Analytics suite. Lots of other algorithms, as you might expect, like connectedness and adjacency and page rank and shortest path, etc. But the one we're using today is this one called weakly connected components. And we're going to use that to detect subgraphs in our data. So we submit this job and we get some feedback saying that it identified 137 subgroups or subgraphs within our data set, and each of those subgraphs is approximately 7,090 nodes on average. If we look at the way that data model has changed after having run that graph analytics, we can see that the focus of the model has now changed. We've got a new vertex in the middle here, a blue one. We call this a grouping node. And around that, we've got the data that we looked at before. So within each subgroup, as you expect, we've got one and only one website in green. And again, we've got the items and the sellers that are participating or are active around that around that website in that subgraph in yellow and red. So we've kind of pre-processed our data now. We've made it available and ready for consumption by the machine learning services. And so we can get into the meat of the sort of the iterating through the machine learning process. And on that note, typically the machine learning life cycle is iterative. You load the data, you get the data, you make it usable. You create a machine learning model, you train that model, and then you run that model and you use that model to predict on new items. If you're not happy with the accuracy or the behavior of that model, you can tweak it and change some of the ways that you've constructed the model, and then you can iterate through that process until you're happy with the accuracy and behavior of the model you've chosen. But under the covers, what the data scientist is actually doing is that they're using a whole range of services and processes and metadata and infrastructure that's going to deliver this workflow. There are a lot of underlying moving parts, and we can see that in the next graphic where it calls out the individual technologies. We can see there's a high degree of complexity involved in this process, and even within each individual phase of the process there are multiple moving parts. And it takes effort to set up and configure and maintain those moving parts and just maintain the interdependencies between them. But in contrast, the Arango Data Science Suite really abstracts away all of that complexity, and it leaves the data scientists to focus on their core task of delivering machine learning pipelines and helping them to get their applications live more quickly. And it's worth mentioning actually that that saving in administrative effort in itself is a very strong value driver for the Arango Data Science Suite. That the taking away the need for data scientists to manage all of this complexity so they can focus on their core task. The ArangoDB or the Arango Data Science Suite approach to machine learning, everything is centered around the notebook, like the one we're looking at the moment. The notebooks use Python code. But it's largely a low-code approach to machine learning, as I mentioned. Leveraging those magic functions I mentioned before that take away some of that underlying complexity. And the notebook uses the GraphML APIs to drive the orchestration of the services via these APIs, and then those APIs will utilize these underlying featurization, training, and prediction services, but using the data that's held in the Arango database. But like I said, the key takeaway here is that the service and infrastructure orchestration is completely transparent to the data scientist. So if we look at the workflow when we're using the data science suite, it's typically 5 steps. The first one is a one-off. It's project creation. We need something that's going to be a container to accommodate all of the history of the work that we're doing, metadata, etc. So we need to create a project, and we do that, and that then puts us into the full machine learning lifecycle where we featurize data. That means taking human readable data. And we need to convert that into machine understandable data or machine understandable representations of that data. We train a set of models using the data that we featurized, and then we select the model that we're happiest with, the one that's got the accuracy or behavior that we're looking for. And then we can use that selected model to predict in the future on new or unseen data as it appears on the marketplace. So as I mentioned, the first step is to create a project that's as a one-off admin task before we get into the featurization itself. And for the featurization process, we're going to use the data in our model that we think is going to be useful in predicting whether or not an item in the marketplace is counterfeit or not. We'll use the attributes in the collections that we have, that's like website and seller and product, etc. And we'll featurize the attributes within those collections that we want to use and create those machine readable encodings or embeddings, as they're called, for each one of those. And then we run that featurized data through a number of data models, through a number of machine learning models, and then we attempt to predict, whether or not a product is counterfeit. So we can then choose the model that has the most the best performance in identifying those fraudulent products. For each of the subsequent steps, we're going to use something that's called a specification. A specification is just really just a JSON dictionary that allows us to specify the parameters and the controls that we're going to use in the job that we're going to submit. And as we can see here in this featurization specification, we're specifying a number of vertex collections. Here we've got product, person, data, website, and person. And then for each of those collections, as I said, we specify which features we want to use for this process, and we repeat that for each of the collections. And then for each of those attributes, we also need to say what feature type they are, what type of embedding we want to create, whether that's a text or a category or a Boolean or whatever it may be. And we can see here that we've selected or we've specified title, that's just text. So we've called it a text feature type. Same for location, again, that's just text. Marketplace region and currency, they're both a finite list of items. There's only so many currencies that could be used. So they're ideal for defining as part of a category, a bit like a list or a dictionary, if you like. And we do the same thing for all the other vertex collections. But note also that we've got this one specified here, and we've specified that one as a label. And what this does is it sort of informs the system that this is the attribute that we want to predict. This is the one that we want to be able to identify the fraudulent status or whatever of the item. So again, we submit that job. We get some output. It's really just confirming what we've put in. bit of confirmation of job success at the end. And then, as it says here, really, every document of every collection that has been specified in the featurization specification now has new attributes. More specifically, these are the machine understandable representation of the features we selected. So in the product collection, we've got a number of new attributes that appear to have been created by that featurization process. We've got the four attributes that we identified as features that we wanted to embed. So we've got title, currency, location, and marketplace. And as it says, the text embedding of title and category embedding of currency, and the same for the others. And then there's a couple more that we're interested in here. Fraud X. This is a composite embedding, an aggregation of all the other embeddings above, the other features into one composite or aggregate embedding. And also fraud Y, which is, excuse me, a numerical, as it says, a numerical representation of that condensed tag. So at this point, we've successfully completed the featurization process. We've taken our human readable data and we've translated that, if you like, into machine readable representations of that data that are called embeddings. And we're now going to use that featurized data to train a model to predict the correct values for us. If we go down to the training section, then the graphic here really sort of calls it out. We're going to feed the training data into the model. We're going to allow the model to learn some patterns. We're going to tune the model parameters to minimize the number of errors and to try and get the best accuracy, and then choose the best model for our purposes. And we're going to, as I said before, it's iterative, so we'll go through this as many times as are needed until we're happy with the accuracy of the model that we've chosen. We've got a specification for the training job that we're going to submit. It's much more concise than the one for featurization. We're simply saying we want the output of the featurization process to be the input for this task. The machine learning spec we're going to use is saying that we want to use node classification. That's the model that we want to run. The product collection is the one that contains the data that we're interested in, and in particular, Fraud X and Fraud Y is the input feature, that composite embedding, and Fraud Y where the label has been created. So once we've submitted that training job and allowed the models to process that featurized data, we can then decide which is the best model for our purposes, and we can choose that best model. That model selection process is, the models we choose we can choose based on a number of criteria. What we're choosing here is the model that has the best test accuracy. If we look at the output for the model that has the best test accuracy, at the top it's validation, but we scoot down to the test section. We can see that test accuracy on our first pass is 80.25%, which is actually pretty good for a first pass in machine learning terms. And it's a good basis for further work to try and increase and improve the accuracy of that model. What that output also gives us is something called a confusion matrix down here. Which is a lot of numbers and not immediately helpful, but we can use some Python to represent that visually. We get a visualization of that confusion matrix. And the confusion matrix really, it just serves to help us understand how the model is behaving and more easily see things like false positives and false negatives. The rows here represent the actual values for our label. Ranging from 0 to 12, so there's 13 possible values. I believe that 1 is the value for a counterfeit item. Columns are what the model has predicted, so that we can see here that the model has predicted correctly 26,876 items are counterfeit. However, it has incorrectly identified 1,264 items as what might be empty boxes, for example, in one of the other categories. So what we're really trying to do here is we're really trying to maximize the results in the diagonal and see very strong correlation with the diagonal and minimize the errors falling either side of that diagonal. One thing to be aware of, though, is if you get 100% results in the diagonal and everything's absolutely perfect, it probably suggests that there's a problem with the data that you're using for your featurization and training, and perhaps you're submitting data which already knows whether a product item is counterfeit or not. So that would be a bit of an alarm bell. But the idea is to get as much as possible of the results showing up in the diagonal. So once we've completed that, we're ready to move on to prediction, which is effectively sort of testing how well our model is going to behave. And again, we've got a graphic here which kind of tells us what we're going to do. We need to feed that data into the trained model. We're going to generate predictions using that model. We're going to assign new labels to each product, and then we're going to evaluate how accurate those predictions were. Again, a very concise specification for to submit this job. We just give it the name of the project, the database name, the model ID, because that's got all the other information associated with it already. And lastly, this is a key. We're saying that when you run this prediction, I want you to create a new attribute in that source collection, that product collection, called predicted condensed tag, and put the prediction in that field there. So we submit that job. It doesn't take too long to run. Not much output, but it does tell us that we've now predicted on 341,000 documents. And at this point, our prediction job is completed. And just like featurization, we've written back to the original document with some new attributes. Primarily, this is the one we're interested in, the predicted condensed tag. This is our prediction of whether or not an item is fraudulent or counterfeit. What's interesting here is this output is taken from that fake watch, and it shows us that the fake watch was accurately predicted as counterfeit. So it's pretty reassuring to see that our model is behaving correctly. So at this point, we could go ahead and deploy this model into production, and we could use it to automatically featurize and predict the status of any new products that are added to the site. And here's an example. For example, that's been done on this Toyota key fob that's been submitted. Again, bit of a clue in the thumbnail cache there. Whoops, bit of a clue in the thumbnail cache. It's not where you would expect it to be coming from. And not surprisingly, this item has also been labeled as counterfeit by the prediction job. So, as I said, we could now deploy this model, and we could use it to in a production mode to assess and predict on new items as they're added to the site. Okay, so that completes the machine learning and part of the presentation. Moving now on to the Gen AI piece. We've now got information that's in our database, and we want to be able to use a large language model, an LLM, to be able to read that data from the database using AQL. Would be the most obvious way to read the database from the database, using AQL. But we don't want to have to be responsible for writing the code for those queries. We want to be able to use natural language, and we can use the LLM to write the queries and read the data from the database for us. And we achieve this using integration with something called LangChain, which is totally agnostic to the LLM. You can use publicly available LLMs, or if security is an issue, you can deploy your own LLM internally. But what the LangChain integration does is it allows us to enter those natural language queries and have them processed by the LLM. And we can see an example here. We've got an example in this snapshot of the UI where the question is being asked, who are the sellers that are most likely to be selling counterfeit products? And we've got a really nice structured English answer that's come back to us. And we can train the LLM with a number of AQL statements that will, we can use to query the data. And that's what we see here, the training of the statements that were submitted and seeing the answers that come back. But the upshot of this process is that, we can enter a natural language question in the UI. We use LangChain to interact with the LLM. The LLM then generates the AQL query. The LLM then executes that query. and it returns the result in a JSON format. And then another LLM can then translate that JSON into a block of human readable text for us. And if we go to the bottom, I think the query that we looked at in that box is somewhere around here. Yeah, here. So here's the original question. Who's the sellers most likely to be selling counterfeit products? So the LLM generated this AQL query for us and submitted that, and then an answer was returned. We get a response back, and it's this block of JSON formatted data, and then the LLM reformats that and then presents that back to us in a block of code, or sorry, a block of text in English that is readily easy to understand. So this is really powerful stuff. We've seen how now we can use an LLM to read the data from the database and generate the queries for us. Moving on now to the summary. Hope I haven't taken up too much of your time. Moving on to the summary, just to recap what we've seen today, we've used the Arango Data Science Suite to extract insights from our data from the source graph using graph analytics. We've then trained a set of models, ML models, to predict counterfeit items, and then we've built our natural language interface with Gen AI to talk to the data. So just in summary, I guess, what's the value of this? Well, the Arango Data Science Suite gives data scientists the tools that they need to build and deploy machine learning pipelines. So Arango's streamlined machine learning ops mean that there's no need for data scientists to manage infrastructure and services themselves. They can focus on their core data science responsibilities. They can accelerate the data science process, be more agile, bring applications to market more quickly, and it's a great result for them. The Gen AI integration means that your users can deploy apps that interact with the data using natural language, so they don't all need to be Python or AQL coders to get meaningful information and insights back from the data. And all of this was created and managed within a familiar Python notebook experience running on the Arango platform.